Welcome back to the Deep Dive. Today we're going beyond the surface level, taking a massive stack of technical sources, regulation documents, component specs, and critical design reports. And we're going to distill them into a single, cohesive strategic plan.
That's right. Today, we're effectively operating as chief systems engineers at a major automotive consultancy. Our mission is, well, it's singular, to develop the definitive engineering requirements specification, or SOR, for the next generation of micro low-speed electric vehicles, LSEVs.
And we're tackling what the industry calls the cost-safety paradox.
We are. It's a real challenge.
In that paradox, it's pretty brutal, isn't it? I mean, you're looking at vehicles that have to sell for under $10,000.
Right.
Yet they're now being required to meet high-voltage safety standards. You've got GB 1D3804 in China, FMVSS 305 in the U.S. that were originally written for, M1 class full-scale passenger cars.
Exactly. We're aiming for B-level functional safety, but within these just extreme cost constraints, it is the ultimate engineering problem.
So what's our objective today? What are we building?
Our objective is to guide a development team on building what we're calling a lean HV architecture. We need ironclad requirements for the 6-core high-voltage subsystem.
Okay, let's list them out.
It's the high-voltage interlock loop, the HVIL, the insulation monitoring device, IMD. Then you have the manual service disconnect, or MSD, the fuse, the contactors, and, of course, the entire HV wiring, harness, and connector system. We're literally writing the rulebook from first principles.
This sounds like a really high-leverage exercise. So before we even look at a single component, what's the single most critical strategic decision that shapes this entire architecture?
It's the voltage platform choice. The critical insight we're going to justify throughout this deep dive is that the 96-volt to 150-volt DC platform is the strategic sweet spot.
The sweet spot.
It is the optimal balance point. It allows manufacturers to achieve full regulatory compliance, robust performance, and all without incurring the massive component cost penalties you see with the standard 400-volt or 800-volt EV architectures.
So that's the foundation of the lean design.
It is. Everything builds from that decision.
Okay, let's unpack this. We should probably start by establishing the non-negotiable legal limits. We need to identify that global red line, the regulatory landscape that defines our minimum safe design.
Absolutely. When we're analyzing the LSEV market, we have to acknowledge its history. I mean, these small vehicles thrived for decades because they operated in this kind of regulatory gray zone, especially around their power system.
Right, they were sort of under the radar.
They were. But China's implementation of GB 1E384 2020 changed all of that permanently. It made them the de facto global benchmark for technical compliance.
So how exactly did that standard pull these micro LSEVs out of that gray zone? What was the regulatory pivot?
The standard mandated that any vehicle operating above 60 volts DC must now adhere to stringent B-level voltage protection.
So this isn't just about warning labels anymore.
Oh, no, not at all. It requires mandatory physical and electrical isolation measures. Specifically, it introduced really clear requirements for both direct and indirect contact protection.
Okay, can you break that down for us? What's the difference between direct and indirect contact protection? And what does that mean for component design?
Sure. So direct protection is about preventing personnel from physically touching any energized parts. Simple as that. This is enforced through component ratings like IPXXB.
Which is for finger access, right?
Right. It ensures protection against accidental finger access. Or IPXXD, which guards against a wire or a tool touching something live. Basically, if you can physically get to the HV bus bar, the design has failed a fundamental safety test.
And indirect protection.
Indirect protection deals with what happens if there's an insulation failure. A leakage of high voltage from the conductor to the metal housing or the chassis. This is handled primarily by the grounding system and, crucially, by insulation monitoring.
And you highlighted mandatory active insulation monitoring as the real game changer here.
Absolutely. It is. Previously, a manufacturer might have relied on simple passive checks or, a warning label. Now, the system must constantly monitor the high voltage bus burst to ground resistance in real time.
So it's a dynamic, constant check.
Constantly. This dynamic monitoring capability means the vehicle has to react immediately to a developing fault. We can't rely on delayed or manual checks anymore.
Let's pin down those failure thresholds then, because those are the hard numbers for our IMD design.
The critical thresholds are, for DC high-voltage systems, the requirement is 100 ohms per volt. For the AC side, that's the output of the motor controller or inverter, the threshold is higher, at 500 ohms per volt.
And that ratio is not negotiable.
Completely non-negotiable. It dictates the precision and the sensitivity of our insulation monitoring device. This move away from the old passive methods is critical for detecting some really insidious faults, which we'll definitely get into in more detail later.
So the system has to be constantly auditing its own health. But the environment itself is also a threat. I noticed the GB standard forces environmental toughness validation, things like vehicle weighting and cleaning tests.
Yes, and this has a huge impact on the physical design choices for connectors and enclosures. The demands for components to meet IP67 or even the highly stringent IP6K9K standard are now mandatory for key components.
Like the manual service disconnects.
And all the HV connectors, yes.
IP6K9K, that's a really tough rating. For our engineering teams listening, what does that actually mean in performance terms?
Well, it's not just surviving rain. It means surviving high-pressure, high-temperature jet sprays, the kind of punishment you might see in an automated truck wash or, simulating the dynamic impact of water during deep weighting.
So if water gets in?
If even a tiny amount of water gets in, it can severely degrade the insulation resistance. That leads to potential electrical leakage, short circuits, and a serious fire hazard. This standard basically guarantees the electrical integrity against environmental abuse, which is a huge factor in the long-term reliability of these LSEVs.
So we can't ignore the worst-case scenario, thermal runaway of the battery pack.
Right. GB 38031-2020 addresses that existential threat head-on. The Battery Management System, the BMS, is now mandated to issue a thermal event warning at least 5 minutes before the actual cell thermal runaway occurred.
5 minutes? That doesn't just demand accurate thermal sensing, does it?
Not at all. It mandates that the entire high-voltage safety system, the BMS, the HVIL, the contactors, must all maintain operational integrity, even when the battery is entering a critical high-temperature fault state. It ensures the system can at least attempt isolation in those final moments before destruction.
So China sets the mandatory baseline. How do Western and Japanese regulations converge, or I guess diverge from that? Do we have to design 3 separate safety systems?
Fortunately, on core electrical safety, there's a remarkable convergence. The U.S. FMVSS 305-305A, for example, focuses very heavily on post-crash safety. The emphasis is on neutralizing the hazard after an impact.
How quickly did that hazard have to be neutralized?
They allow 60 seconds. Post-crash. Within that minute, the system has to achieve one of 2 outcomes. Either the high-voltage source is completely isolated from the chassis, or the bus voltage has to drop below the non-hazardous levels of 60 volts DC or 30 volts AC.
So that drives the need for really fast contactors.
Fast-acting contactors and sophisticated active discharge capabilities, which are usually integrated into the motor controller. It's all about making sure that residual energy is bled off the bus capacitors very, very quickly.
So in the U.S., the challenge isn't just absorbing the impact, but designing a safety sequence that executes flawlessly under, well, chaos.
That's a perfect way to put it. Then in Europe, you have the UNECE R100 standard. And while L7E vehicles, heavy quadricycles, have less demanding passive safety or collision requirements than full M1 cars, their electrical safety mandates align perfectly with the Chinese benchmark.
100 ohms per volt DC and 500 ohms per volt AC.
Exactly the same.
In Japan. I know JSO standards often focus on quality and maintenance.
They do, and they add a crucial detail about personnel safety. Beyond the standard stuff about reliability against vibration and thermal shock, Japanese labor laws mandate finger-safe protection IP2X for any parts accessible during routine maintenance.
And that specifically calls out the MSD.
Specifically, it requires that the manual service disconnect socket be protected when the MSD itself is withdrawn. It's a small detail, but it's a costly physical design detail that we absolutely have to incorporate into our spec.
So the takeaway is clear. Regardless of the vehicle size or class, the performance bar for HV safety is now set by M1 standards. And the micro EV segment has to achieve this within these, almost impossible cost limits.
Right. So now we have to transition to the practical reality. How are the successful manufacturers actually balancing this?
Okay, so to develop a lean HV architecture, we've got to analyze the strategic compromises that market leaders are making. Our sources point to 2 diametrically opposed strategies. The Wuling Hongguang Mini EV,
which basically owns the high-volume cost market,
and the Citroën Ami, which chose that ultra-low voltage route. Let's start with Wuling. Their strategy is centered on extreme cost control, and specifically their choice of the 96 to 144 volt platform. You called this strategically brilliant. Why?
It's brilliant because it minimizes the bill of materials, the BO&M cost, on the most expensive components in the entire system, the power semiconductors.
Okay.
The choice of 96 to 144 volts perfectly avoids the need for what I call the 400-volt tax.
The 400-volt tax, what exactly is that?
The moment you cross that 200 to 250-volt operational threshold and move toward 400 volts, you are forced to use highly complex and expensive components, things like silicon carbide or SENSIC or advanced IGBTs in your motor controllers, your inverters, your onboard chargers.
And those are needed to handle the higher voltage efficiently.
Exactly. They're wide bandgap semiconductors necessary for the high voltage and the power switching efficiency. But by staying below 150 volts, Wuling can leverage cheaper, higher volume, and much more mature 200 to 250 volt silicon-based MOSFETs.
So the material cost difference here must be substantial. Can we put a number on that saving?
Oh, absolutely. The raw cost difference between a high-power 600-volt SiC module and a comparable 200-volt power MOSFET module can easily be a factor of 10, sometimes even more, especially when you factor in the cooling requirement.
A factor of 10. Wow.
This choice alone provides a massive cost advantage. We estimate it's about a 30% reduction on the overall HV component cost portfolio.
How did that cost-saving imperative show up in the battery pack structure itself?
They use a cell-to-pack, or CTP-style design. This eliminates the need for internal battery modules and all the associated high-cost module connectors, internal wiring, and complex hardware that you need to manage those submodules. It reduces manufacturing complexity and, potential failure points like contact resistance.
But every strategic choice has a trade-off. What's the consequence of that CTP design and that extreme lean structure?
The primary trade-off is serviceability and repair. A CTP design often means a highly destructive disassembly process for any kind of repair, which usually makes pack repairs totally uneconomical.
So the philosophy shifts to replace the whole pack.
Replace the pack, don't repair the module. And for the HVIL topology, they stick to the simplest, most economical solution, a hardwired series daisy chain. It meets compliance, but like we said, it has very limited diagnostic capability compared to the more sophisticated systems in luxury vehicles.
Okay, now let's look at the Citroën Ami. They went for the opposite extreme, 48 volts. It seems like the ultimate cost avoidance strategy, right? Sidestepping that 60-volt DC threshold altogether. So why did you call this the low-voltage paradox?
Because while they do avoid the high-voltage shock regulations, they introduce severe new problems. Problems related to fundamental physics, specifically current management. The paradox comes from the power equation, P equals V times I.
Right, power equals voltage times current. So if you want the same useful power, say 6 kilowatts, and you drastically reduce the voltage,
the current has to increase proportionally. Exactly. Let's just crunch the numbers. A 6-kilowatt motor operating at 144 volts requires a current flow of about 41.7 amps.
Okay.
Now, drop that voltage to 48 volts. That same 6 kilowatts now requires 125 amps. That is a threefold increase in operational current.
And that massive increase in current requires much thicker copper wires.
Much thicker, heavier, and far more costly. The required copper gauge for 125 amps is huge compared to 40 amps. We're talking about a dramatic increase in cable cross-sectional area, which adds weight and bulk to the harness.
And the heat must be a nightmare.
Infinitely harder. High current running through connectors, terminals, contactors. It generates resistive heat, what we call I²R losses. This heat accelerates connector degradation, increases contact resistance, and requires bulkier, heavier heat sinks or even dedicated cooling loops.
So they save on the semiconductors.
But they pay a hefty price in copper, weight, and thermal management complexity. It often results in an architecture that's heavier and less reliable in the long run. The cost savings on the chips are potentially nullified or even surpassed by the cost of all that extra copper and heat dissipation hardware.
And you mentioned a secondary challenge with grounding.
The grounding complexity is the Ami's second major technical headache. These LSEVs frequently use non-conductive materials, plastic, fiberglass, composites, for the body panels to save weight and complexity.
So if the chassis isn't conductive metal, you lose the standard ground return path.
You do. A traditional car uses the metal chassis as the negative terminal return path, which simplifies the harness. The Ami can't do that. It has to employ a dedicated return wire for the negative circuit, running parallel to the positive high current cable throughout the vehicle.
That sounds complicated.
It massively complicates the harness architecture, it increases the wire count, and it forces engineers to design a fully isolated electrical system where the ground is manufactured, not just inherited. This adds weight, complexity, and cost, directly undermining the whole point of the 48-volt platform.
This benchmark analysis gives us a really clear strategic directive for our SOR then.
It absolutely solidifies the choice. Our SRR will define all requirements based on that 96 to 150 volt platform. It is the best balance point. It reduces the massive current and thermal issues of 48 volt systems, while at the same time capitalizing on the cost savings of 200 volt components versus the 400 or 800 volt systems. It's the only real pathway to achieving those mandatory B-level safety requirements within that sub $10,000 commercial constraint.
Okay, platform established. Let's design the nervous system. Starting with the high-voltage interlock loop, the HVIL. We mandated that hardwired series daisy chain architecture because it's the most cost-effective.
Yes, the topology requirement for our SOR is that hardwired series daisy chain, VCU or BMS to the MSD, then through the MCU, the OBC, the PDU, and finally back. It minimizes the physical wire count. But the integrity of the signal running through that loop is where we leverage intelligence over cost.
Right, and this is where we need to slow down and explain the technical detail that separates safe from dangerous, why our SRR mandates a PWM signal and explicitly prohibits a constant DC voltage.
This is a critical functional safety requirement. It addresses what we call silent failure modes. Imagine using a simple DC signal, a steady 12 volts, to confirm the loop is connected. It's basically a light switch. Either it's on or it's off.
So if the signal is constantly on at 12 volts, the system thinks everything is fine.
Exactly. But what happens if a wire chafes and that 12-volt line accidentally shorts to a nearby power source, the high voltage itself or the low voltage battery, a condition we call a short-to-power fault?
If it shorts to power, the signal remains 12 volts, so the system still sees the light switch as on.
Precisely. The system is falsely interpreted as normal, even though the integrity of the loop has been physically compromised. It's a silent, dangerous failure that provides zero warning. A maintenance worker could pull a connector expecting the system to de-energize, but that short-to-power fault is masking the physical disconnect.
But a PWM signal, a pulsed width modulated signal, solves this. It's like it requires a handshake.
That's a great analogy. We specify a PWM signal, maybe 12 volts operating at 50 to 100 hertz with a 50% duty cycle. The controller isn't just looking for 12 volts, it's looking for a specific rhythmic pulse sequence.
The secret handshake.
The secret handshake. If the line shorts to a constant power source, that pulse pattern disappears. It's replaced by a steady, continuous 12-volt line. The VCU instantly recognizes that the expected pulse integrity is missing, which allows it to unambiguously distinguish four critical states: normal, open circuit, short to ground, and that really dangerous short to power fault. That level of diagnosis is crucial for functional safety.
That makes the HVIL a smart network, not just a simple wire. Now, moving to the physical protection at the service point, the connectors, we're requiring last mate, first break.
This is a mechanical requirement to prevent destructive arcsing under load, which can injure people or damage components. The core spec is simple. The HVIL pin must be physically shorter than the main power pins.
And what's the necessary reaction window for that?
The SRR demands that the HVIL circuit break at least 20 milliseconds before the main power terminals physically separate when a technician pulls the plug.
So that 20 milliseconds is the temporal failsafe.
It is. It gives the BMS the time it needs to detect the HVIL break, trigger the contactors to open, and effectively interrupt the high current flow. If the current is broken after the main pins separate, you get a massive, potentially lethal arcing event. That 20 millisecond margin is critical.
That is a highly leveraged engineering decision.
Okay.
Let's move to the second major sensing component, the installation monitoring device, the IMD. We mandated active signal injection.
Correct. And we must explicitly prohibit passive balanced bridge methods. They possess a fatal inherent flaw that makes them completely inadequate for modern safety standards, like GB 1300384.
And what is that flaw?
They cannot detect symmetric insulation faults. This is the scenario where both the positive and the negative high-voltage lines leak electricity equally to the vehicle chassis or ground at the same time.
Which is a very common failure mode in the real world.
Very common, especially if the battery pack is sitting in conductive fluid saltwater ingress during waiting, or even a pool of conductive coolant or road dirt.
So if I have equal leakage on the positive and negative sides, the passive bridge remains balanced, and the IMD stays silent even though the chassis is now energized.
Precisely. The system is completely blind to that specific common failure mode. By mandating active signal injection, the IMD actively imposes a known, controlled signal onto the high-voltage bus bar, and then it measures the resistance of the return path to ground. This active probe allows the system to detect both non-symmetric and symmetric faults with equal accuracy.
how do we manage the cost of this more sophisticated active component in our lean architecture?
Integration, that's the key. The SOR recommends integrating IMD functionality directly onto the BMS mainboard, leveraging the existing microcontrollers and communication hardware.
So that eliminates the cost of a dedicated enclosure, a separate connector?
And redundant wiring harnesses. It streamlines the manufacturing process and actually improves reliability by reducing the component count.
Let's define the performance requirements, using our 144-volt platform as the example.
Okay. We need a wide monitoring range, 0 kiloohms up to 10 megaohms, with high accuracy, better than plus or minus 5% in that critical detection range of 100 kiloohms to 1 megaohm. And more importantly, the response time has to be swift. Less than 10 seconds for the IMD to flag a sudden resistance drop to the fault threshold.
And applying the dual-stage alarm system to our 144-volt vehicle.
Our warning, the yellow light, is set at 500 ohms per volt. For 144 volts, that calculates to 72 kiloohms. At 72K, the system flags a mandatory maintenance issue and limits power output, but the vehicle remains operational. It lets the driver get to a service point safely.
And the red line fault stage.
That's the regulatory minimum, 100 ohms per volt. That translates to 14.4 kiloohms for the 144-volt system. When the insulation drops that low, the risk of lethal shock or system failure is just too high. The SR mandates immediate high-voltage shutdown or, at the very least, a prohibition of restarting the system until the fault is repaired.
And finally, the self-diagnosis of the IMD itself. A sensor is only useful if we know it's alive.
Absolutely. We mandate that the IMD execute a self-test during every single power-up, every KL15 on. It uses an internal switch to simulate a known leakage resistance, say 20 kiloohms, and it has to confirm that it can correctly detect the simulated fault.
And if it fails its own test?
If an IMD fails its own test, the BMS must prohibit the closing of the main contactors. It prevents high-voltage engagement entirely, ensuring the monitoring system is functional before the vehicle can be driven.
Okay, we're transitioning now from sensing the hazard to providing the physical means to interrupt it. Let's start with the manual service disconnect, the MSD. This is the crucial physical safety device for maintenance personnel and first responders.
The MSD is often overlooked in early design, but its complexity is really driven by these regulatory demands for ingress protection and personnel safety. Location-wise, it has to be easily accessible, often integrated into the battery pack lid like the Wuling benchmark, and it must consolidate the main fuse.
Right, so consolidating the main fuse into the MSD housing simplifies the power distribution unit, the PDU, saving cost, and terminals. But the safety rating is complex because it depends on the MSD state, doesn't it?
Exactly. When it's inserted and locked, the MSD unit must meet IP67 and IP6K9K to satisfy those environmental toughness mandates. However, when the MSD is withdrawn, the remaining exposed terminals, the socket must be IK2XB, finger safe.
And that protects personnel from accidental contact.
Yes, if they haven't properly checked that the high voltage has been isolated elsewhere. That IP2XB rating is a direct response to labor safety standards, particularly those we saw in the Japanese JSO requirements.
And how do we ensure the power is broken before a human hand physically pulls the main contacts apart? This has to connect back to our HVIL logic.
It requires a mechanical and electrical safety logic integration. We mandate a two-stage unlocking mechanism.
2 stages.
The first stage, the unlock action, must physically and mechanically trigger the HVIL microswitch. That ensures the BMS has that requisite 20 milliseconds to command the main contactors to open. Only after that interruption command is sent and executed can the second stage, the physical withdrawal of the main contacts, take place.
So it prevents the operator from manually separating energized contacts.
It completely eliminates the risk of physical arcing damage.
Okay, moving to the ultimate failsafe, the fuse system. We rejected pyro fuses for cost reasons, so our SOR specifies high-speed DC fuses. What are the key characteristics we need here?
We need fuses with AR or GR characteristics. We should avoid standard automotive blade fuses entirely. They're just not rated for the high DC voltages or the interruption capacity we need. We mandate a rated voltage minimum of 500 volts DC.
Even though our system is only 96 to 150 volts.
Even then.
I have to challenge that. Why specify 500-volt rated fuses if our bus bar only hits 150? That feels like expensive over-engineering.
That is a legitimate challenge, but it's a calculated strategic choice based on supply chain maturity. The 500-volt DC-rated fuses are mass-produced and highly leveraged across existing medium-voltage EV and solar platforms. This maturity ensures better procurement costs and availability than trying to source some niche 200-volt high-interrupting capacity fuse.
And it future-proofs the design.
It does. It allows our client to potentially upgrade the voltage platform slightly, maybe to 200 volts, without requiring a complete component requalification.
Okay, that clarifies the strategy there.
Yeah.
Now, current sizing. Let's take a 25 kilowatt motor at 96 volts.
That requires about 260 amps of operating current. We have to size the fuse to handle that, but also apply severe derating factors for temperature and lifespan.
Right.
So the SOR would mandate a selection rating between 300 and 350 amps, ensuring it doesn't blow during normal high-power acceleration, but still protects the system.
And the most critical aspect of the fuse is its interrupting rating, its braking capacity.
Right.
This dictates the maximum catastrophe the fuse can contain.
Absolutely paramount. For LFP battery chemistry, the short circuit current can be massive, often reaching between 5 and 10 kiloamps. That's 5,000 to 10,000 amps. Our fuse must be rated to safely interrupt that current level.
Which is why you need ceramic tube fuses.
Exactly. Specialized arc quenching material. A standard blade fuse which just instantly explode under that kind of short circuit.
Let's circle back to the pyro fuse decision. You chose to substitute it with a much cheaper ceramic fuse. Are we making a safety compromise there?
We're making an intelligent risk optimization. Pyro fuses, which can cost upwards of $50, react negligibly faster than modern high-speed ceramic fuses at this voltage level. Our decision matrix shows that unless the battery's short-circuit current exceeds the weld-breaking limit of the main contactors, which is typically above 10 kA for the contactors we specify, the $5 ceramic fuse provides functionally equivalent compliant protection at an 80% cost reduction.
So we're not compromising compliance, we're optimizing cost.
Optimizing based on the system's actual electrical limits.
That's a highly leveraged trade-off. Finally, the high-voltage contactors, the relays that connect and disconnect power under load.
We mandate the standard 3-relay configuration for redundancy and safety, a main positive, a main negative, and the essential pre-charge relay with its limiting resistor.
Why is that pre-charge logic mandatory? What's the specific danger we are preventing by forcing that sequence?
It's mandatory to prevent destructive inrush current surges. When you close the main contactor, the motor controller's bus capacitors are essentially empty. Closing that main contactor directly onto that discharged bank creates a momentary controlled short circuit, generating a massive current flow.
And that inrush surge can physically melt or weld the contacts shut.
It can. And if the contacts weld shut, the driver loses the ability to isolate the high voltage in a fault condition, creating a persistent, potentially lethal hazard.
I see.
The pre-charge sequence forces the current to flow first through a limiting resistor, which slowly charges those bus capacitors. Once the voltage is equalized, the main positive contactor closes, and there's no destructive surge. This sequence protects the contactor itself, which preserves the vehicle's fundamental ability to electrically isolate the high-voltage source in an emergency.
And what technical specs ensure these contactors can safely quench the arc when they open under load during an emergency?
Arc quenching is their core function. They have to be hermetically sealed, usually with a ceramic braze or epoxy, and filled with an inert gas like a hydrogen-nitrogen mix, or operate under a vacuum. This environment is necessary to absorb or cool the high-energy arc that forms as the contacts pull apart, preventing the arc from sustaining itself.
Which would otherwise lead to catastrophic failure.
Catastrophic failure, burning, or welding of the contacts. We prioritize suppliers with validated designs, like Hongguang. Their HFE82 series is proven in millions of low-voltage production EVs.
Okay, we've established the components. Now we have to define the physical integration. We need robust requirements for the wiring harness, the connectors, and the crucial and often misunderstood grounding system for these vehicles built with non-conductive bodies.
We start with the physical wire harness. Identification is simple. The outer sheathing must be orange, RAL 2003, for universal HV recognition. But the real technical challenge lies in managing electromagnetic compatibility, or EMC.
All right, in a micro LSEV, everything is packed so tightly. The high-voltage power lines, especially the three-phase AC lines going to the motor, they create massive high-frequency noise EMI that can corrupt the sensitive VCU and BMS low-voltage signals running nearby.
And that noise is generated by the high-voltage chopping, the PWM switching. To suppress it, we mandate comprehensive EMC shielding. A braided copper shield layer with greater than 85% coverage around the conductors. And critically, this shield must be connected 360 degrees circumferentially to the connector shell.
Why the 360-degree connection? Why can't we just attach a small ground wire?
A small ground wire creates what's called a pigtail connection. It actually acts as an antenna for high-frequency noise, which makes the shielding ineffective at higher frequencies. The 360-degree connection, a full circumferential bond to the metallic shell, creates a true Faraday cage effect.
So it channels the EMI noise away.
It channels the noise away from the conductors and into the housing, ensuring those sensitive digital communication signals stay clean. This is an area where cost is often cut, and it leads to intermittent software and communication errors down the line.
Let's talk about sizing these wires. Given the tight, often unventilated packaging of these micro LSEVs, how does that impact the necessary cable gauge?
It requires severe current derating. Standard ampacity tables are based on open air or, standard passenger car ventilation assumptions. In a micro LSEV, we have to assume a compact, hot layout. So our SR mandates using severe derating factors, referencing standards like NASA or ISO 19642, and setting the ambient temperature for calculation aggressively high, somewhere between 85 and 105 degrees Celsius.
What does that mean in practice? Does a 40-amp line need a wire gauge that's actually rated for 60 amps?
Exactly. You have to select a cable with a much higher theoretical current capacity than the application requires, simply because it lives in a hostile, hot, cramped environment. This increases the cable size, weight, and cost, but it's absolutely necessary to prevent thermal degradation of the insulation over the vehicle's lifespan.
And physical protection.
Orange PA6 corrugated conduit for full coverage, with fixing points every 200 to 300 millimeters to prevent strain and vibration-induced chafing.
Now we have to address the biggest architecture challenge that's unique to this segment: the grounding strategy for composite bodies. If the body is plastic, where does the fault current go?
This requires us to engineer a virtual chassis, which we call equipotential bonding. Since there's no inherent conductive chassis, we have to establish a dedicated artificial network, a grounding bus bar, or a complex harness network to create a network of equipotential connection points.
And what's the critical safety rule for this network?
The SOR mandates that all conductive external metal housings of high-voltage components, the motor shell, the MCU housing, the OBC casing, the battery box, must all be connected to this common grounding point, usually with highly conductive braided copper straps or dedicated yellow-green wire.
And the specific resistance requirement is the absolute red line here. What is that number, and more importantly, why?
The resistance between any two conductive external metal enclosures on the vehicle must be less than 0.1 ohms. This is mandatory under both GB 18384 and UNECE R100.
Can you help our listeners understand the physics of why 0.1 ohms is the critical number for preventing lethal shock?
It ties directly back to Ohm's law and the maximum permissible touch voltage for a human. If you have an insulation failure, say 100 volts felt onto the chassis, and the resistance between 2 points a person could touch is high, the touch voltage across those 2 points becomes dangerous.
So even if the chassis is energized, if the resistance between the battery box and the motor shell is super low,
the voltage potential between them is also super low. By guaranteeing the resistance is less than 0.1 ohms, we ensure that in the event of any single insulation failure, the maximum potential difference a person could touch between any two external points is kept well below the threshold for dangerous current flow, which is typically around 50 volts.
So the low resistance ensures that if one part of the vehicle becomes energized, the current immediately flows through that engineered low resistance path and trips the fuse, rather than waiting for a human body to provide a secondary path.
Exactly. It's a critical life-saving design element. And if you're using CFRP carbon fiber reinforced plastic, you have to use specialized conductive gaskets or metal inserts to ensure reliable contact, because the resin layers are insulators. The structural material itself just cannot be relied upon for grounding.
We have a comprehensive, lean SOR defined. Now we have to prove that this cost-optimized architecture actually meets these stringent safety standards. Let's define the key verification tests, the DVP&R steps.
Our validation plan focuses on proving the functional safety systems work under duress. We start with the critical GB 10384 IMD verification test.
This proves our active monitoring system meets that 100 ohms per volt threshold dynamically.
Correct. On a test bench, we simulate the most dangerous fault, a resistance drop right to the critical limit. We parallel a variable resistor between the high-voltage bus bar and the vehicle ground, and we tune it precisely to 14.4 kilo ohms for our 144-volt system.
And the pass-fail criterion is severe.
It is. The vehicle must detect the fault, trigger the red warning light, and limit or cut power within 10 seconds. It's a dynamic compliance check.
Okay, next, proving the integrity of the HVIL's temporal failsafe, that 20 millisecond last mate first break logic.
The HVIL effectiveness test. This involves artificially severing any single node, simulating a connector being pulled or a wire being cut while the vehicle is running under load. The main contactors must interrupt the circuit within 150 milliseconds, and the inspection has to confirm there is no significant destructive artensing or welding on the contactor surfaces.
It proves the sequence worked.
Exactly. It proves that 20-millisecond window prevented a dangerous interruption event.
And the environmental sealing verification, proving our IP67 and IP6K9K components hold up in real-world punishment.
We perform the environmental sealing test. This includes high-pressure jet spray and vehicle weighting tests, driving through, say, 30 centimeters of water at speed. Post-test, the insulation resistance must immediately be retested and must remain above that 500 ohms per volt warning threshold. That proves no moisture ingress degraded the electrical isolation. And of course, a physical inspection must show zero water inside the battery pack or component housings.
This brings us back to the strategic core of our SR. We set out to achieve M1 safety at LSEV costs. Let's formally review the McKinsey-style cost-safety optimization matrix that justifies every design decision we've made.
The whole premise is intelligent, high-leverage engineering substitution. We focused on 3 key strategic levers to cut costs without compromising that mandatory regulatory red line.
Lever 1, the platform voltage shift, the key to the entire architecture.
Shifting from 400 or 800-volt platforms to our optimized 96 to 150-volt system, this delivers an estimated 30% cost reduction on high-voltage power components. The savings come directly from replacing those expensive, complex 600 or 1200-volt CCAS modules with simpler, high-volume 200-volt MOSFETs.
Which also have less complex cooling needs.
Right. It simplifies the whole thermal management system.
Okay, lever 2, component integration and harness simplification.
Moving from multiple separate units, your OBC DC-DC PDU, to highly integrated multi-in-one modules. This reduces the number of housings, eliminates complex intermediary harnesses, and it cuts the connector count. Our estimate here is a 15% cost reduction, and crucially, integration actually improves reliability because you have fewer points of failure.
And lever 3, the calculated substitution of the ultimate failsafe.
The calculated substitution of the $50 pyro fuse with the high-speed $5 ceramic AR fuse. It's an 80% cost reduction on that critical component. Because our system's maximum short-circuit current is generally less than the 10 kA threshold that would necessitate the extreme speed of a pyro fuse, the ceramic fuse provides functionally compliant protection while hitting that severe cost target.
The final step of our SOR development is validating the supply chain, ensuring these high-performing lean components can be sourced affordably and reliably.
For this, we recommend leveraging the scale of the established, validated Chinese domestic market, which has matured very rapidly under these GB standards. We need suppliers who can meet the performance specifications we define today.
So who specifically meets the needs of our contactor and fuse specs?
For contactors, we would recommend Xiamen Hongfa, specifically their HF E82 series. It's proven to provide the hermetic sealing and arc quenching capability needed for 150-volt systems under high load. For high-speed DC fuses, Zhongrong Electrical or Sinofuse, and their EV-specific RSZ series meet the necessary 500-volt rated voltage and high interrupting capacity requirements.
And then for connectors?
For connectors, we'd look to high-volume players like Johnfun or regional TE connectivity product lines that can guarantee the necessary IP6K9K and that crucial 360-degree shielding connection.
This level of detail really moved the development process out of guesswork and into a quantified, risk-assessed, and commercially viable engineering framework.
This deep dive really shows that achieving global safety standards in the micro LSEV segment is fundamentally a resource allocation problem. Safety isn't compromised, the engineering is just leveraged more intelligently.
Right.
The key to hitting that $10,000 price point is the intelligent, lean architecture centered around that 96 to 150-volt sweet spot, which allows for the use of cheaper, mature power semiconductors and component integration.
The functional safety, in the end, really rests on those small, high-leverage details we discussed. Things like using PWM for the HVIL to detect those silent, short-to-power faults.
Mandating active IMD to detect symmetrical insulation leakage.
Or guaranteeing that 0.1 ohm equipotential bond across the vehicle's external housings to protect the user from touch voltage.
And if we connect this to the bigger picture, While the 100 to 150 volt platform is the definitive strategic winner for this segment today, technological pressures are, they're relentless. The next evolution probably won't be a jump to 800 volts, which remains cost prohibitive for this segment.
So what will it be?
I think it'll be an increased focus on component integration, moving from 3 separate contactors to a single integrated power module, or adopting wireless BMS and smarter sensors. This raises a really important question for future analysis, though.
Which is,
If manufacturing scale continues to drive down the cost of components optimized for slightly higher voltages, how much longer will the 96 to 150 volt sweet spot last before competition forces the industry to standardize upwards? Maybe towards a 200 or 300 volt architecture to unlock some marginal performance gains.
that is a thought for all of us to chew on. Until next time, we encourage you to explore the requirements of a GB2384 and the principles of equipotential bonding yourself. The future of safe, affordable urban mobility depends on these engineering decisions.